Welcome, everyone. For today's prep, I want to start to look at the next topic, which is reading graphs of the derivative functions and using those graphs to kind of recover information about the original function f. So particularly, in this section, we're going to see if we're given the graph of the first derivative, f prime, for some function f, we'll be able to see how to locate the intervals of increase-decrease for that function f, how to actually find the intervals of concavity as well, how to locate where our function has a high point or a low point, so locating the local max and min, and then also locate any inflection points. So we'll be given the graph of f prime. And we'll also see, and I think this is where we're going to start, given the graph of f double prime, the second derivative, we'll be able to figure out the intervals of concavity for f and locate any inflection points for f as well. So there's a little bit less going on here with our second derivative. So let's start with that. Let's look at the second derivative and see what information we can recover. All right, so we've looked at this before, but if we're looking at an interval, a section of the x-axis, so we're looking at an interval from a to b, if we knew our second derivative is positive on that interval, so it's greater than 0, then we know the original function is concave up there. And if the second derivative is less than 0, so it's negative, well, then we know the original function f is concave down. So this is what we've done with the intervals of concavity. So this is nothing new. Let's look at example 1, though. So we're going to kind of put this in a slightly different context. So here we're given the graph of f double prime. We're given the graph of the second derivative. So this is not our original function. So we're going to be considering the original function. We want to kind of recover the information. What do we know about this function? But what we have here is just the graph of f double prime. So this is what we have, the graph of its second derivative. And let's see what we're going to try to do. Well, we want to find the open intervals where the original function f is concave up and concave down. So again, there's two functions at work here. We have f double prime, the second derivative, and that's where we have all this information. That's what this graph is. We're trying to recover information about the original function. So we want to know where is the original function concave up or concave down. So we know, in order to do this, find the open intervals where f is concave up or concave down, what we really want to do is just get a sign chart for f double prime. And we can do that right on our graph. So let's kind of review the steps. What do we normally do when we're trying to find the intervals of concavity? Well, the first step is we calculate our formula for f double prime. Now, we don't have any formulas here, but we are given the graph, so that's actually enough information. Then we want to look for where the possible inflection numbers. So that was our usual second step. Look for the possible inflection numbers. And there was two possibilities. Either our second derivative could be 0, or the second derivative is undefined. So those are the two things that we're looking for. Where is the second derivative 0, and where is the second derivative undefined? All right, so let's go up to our graph, and let's locate these points. So if we go up to our graph, well, second derivative being undefined, what we would see at an undefined point is there would be a hole on our graph. So that if our second derivative was, say, undefined at x equals 4, there would be a missing point at x equals 4, or something like that. So in this case, there's no place where our second derivative is undefined. Every single point here is included on the graph. All right, so there's no missing points. So the only one we really have to worry about is where is the second derivative equal to 0? Well, this is where it crosses the x-axis. So we want to look at, well, where are the points where we cross the x-axis? And we see 2 of them. So those are our 2 special points. So they kind of split up the x-axis for us. And literally, they're splitting up the x-axis into 3 separate sections. We've got this section, we've got this section, and then there. All right, so once we identify those 2 places, so in this case it's x equals 0 and x equals 3. So those are the 2 places that we have here. Well, then we do our sign chart. Normally we do our sign chart. For f double prime. And our sign chart is just the x-axis. We plot the points that we find, and we list our intervals and then figure out the sign of f double prime on each of those intervals. So let's do this right on the graph. We've got our first interval here. We've got our second interval, and then we've got our third interval over here. And let's write out what those intervals are. So the first interval is going from minus infinity to 0. Then we've got the interval 0 to 3. And then we've got our interval 3 to infinity. And we want to figure out what is the sign of f double prime on each of those intervals. And that's going to tell us about our original function, f. Okay, so let's look at this first interval here. And how do we figure out using the graph if a function is positive or negative? Well, you just look, is it above the x-axis or is it below? So if the graph is above, well, that means you've got positive values. And if the graph is below the x-axis, well, it means you got negative values. So when we look at this section of the x-axis and we look for our graph, we see that the graph is up here, and it's literally above the x-axis. So that means, and because this is the graph of f double prime, that means f double prime is positive, which means we then know that our original function, since the second derivative is positive, the original function must be concave up on that interval. Okay, let's go to the next one. In between 0 and 3, if we look at the section of our curve there, well, it's literally underneath the x-axis. So it's below the x-axis, so our second derivative is negative. And when our second derivative is negative, that means our original function is concave down. And then over on our last interval, we see the graph is back to being above. So that means our function, the original function, is concave up there. All right, so we found our intervals of concavity. Concave up on the first interval and the last interval, and then concave down in the middle. So let's write those out. So where f is concave up on the interval minus infinity to 0 and 3 to infinity, and then f is concave down on that middle interval. And again, it's tricky because we're looking at this graph, and this graph looks like it's always concave up. But we're looking here at the second derivative. So we're not investigating the shape of the graph of the second derivative. We're trying to use this graph to uncover what the shape of our original function is. So yeah, this function itself, the graph that we're given, this is always concave up, but that's not really the function we're entirely interested in. This is the second derivative. We're trying to figure out the concavity of our original function. So it's a little tricky. You have to keep the 2 different functions in mind here. All right, so once we have our intervals of concavity, then we can go back to those possible inflection numbers and determine if we do actually have an inflection point there. And so if we look at x equals 0, And at x equals 3, we just want to make sure, do we actually have a change in concavity? And yeah, we do. So we have both of these. There's a change in concavity. So at x equals 0, we go from concave up on one side to being concave down on the other side. And then at x equals 3, we go from being concave up on one side to concave down on one side to being concave up on the other side. So again, there's a change there. So that means both of these x values that we found, x equals 0 and x equals 3, are inflection points. So we have inflection points at x equals 0 and x equals 3. Now when we look at this, we don't actually have, these are just the x values for our inflection points. We don't have enough information here to figure out the y value. So kind of an important point. We only have enough information here to identify that we do have an inflection point at x equals 0 and x equals 3. These aren't the inflection points themselves, again, because we're looking at f double prime, but this is telling us where our original function f would have an inflection point. So it would have an inflection point somewhere at x equals 0, and it would have an inflection point somewhere at x equals 3, but we don't know how high up or down the inflection point would be. We don't have enough information here. So our derivatives, we can extract a lot of information from our original function from the first derivative and the second derivative, but we can't get everything. So we can't kind of, in this case, get the y values. And spoiler, we'll actually see how to do that later in the course, but that's for a long while away. All right, so I think that's a good breaking point. And what we'll start to look at in class is, well, if we're given the graph of f prime, how do we recover information about our original function f? All right, so we'll see you then. Bye-bye.